Hallo, hallo, hallo. Ja. Okay, guten Tag. Welche Vorlesung ist es? Rechnerstrukturen. Okay, wir kommen zu Rechnerstrukturen-Vorlesung. Professor Teubner hat vor 2 Wochen, die letzten 2 Wochen, über die Befehlsschnittstelle und Befehlsschatz schon gesprochen. So, es war bis dieser Folien, glaube ich. So, wir machen weiter zum die letzten 2 Themen für diese Vorstellung für Instruction Set Architecture. So, next ist die 2 verschiedene Typen von Prozessoren, so Maschinen. Reduced Instruction Set Computers and Complex Instruction Set Computers. So, wenn wir über Befehlssystem zu klassifizieren, dann gibt es 2 verschiedene Maschinen. Eine ist mit RISC genannt, andere ist mit CISC genannt. Okay, RISC steht für Reduced Instruction Set Computers. CISC is for Complex Instruction Set Computers. Okay, so RISC ist, wie genannt, mit Einfachheit und weniger Befehle für solche Entwicklung. Warum braucht man nur weniger und einfache Befehle für solche Rechnungen? Das ist mit folgenden Zielen zu erreichen. Wenn wir einfach RISC-Maschinen benutzen, dann können wir diese Möglichkeit, dass wir hohe Ausführungsgeschwindigkeit bekommen. Wie können wir solche hohe Ausführungsgeschwindigkeit bekommen, kann man später in die erste Woche im Januar Vorlesung kennengelernt. Das ist zuerst mit Pipeline-Vereinbarung und deswegen können wir auch mit einem kleinen Ansatz interner Zukunft pro Befehl bekommen. Und warum ist es ganz wichtig? Das ist, wenn wir jetzt über die Ausführungsgeschwindigkeit gucken, wir können einfach die Programmlaufzeit mit 3 verschiedenen Dingen zu komplizieren. Es ist zum ersten, wie viele Zyklus wie viele Anzahl von den Befehlen wir ausführen sollten für das Programm. So, wenn wir zusammen 100 Befehle ausführen, dann brauchen wir die zusammen 100 Befehle. Und wie viele Cycles per Instruction wir brauchen für jedes Befehl, so Durchschnitt. Ja? So, zum Beispiel, wir haben 100 Befehle, jeder Befehl brauchen wir 2 Zyklen. So, das ist, brauchen wir zusammen 200 Zyklen für das Programm. Und das ist natürlich am Ende auch mit die Dauer von einem Zyklus zu multiplizieren. So, zum Beispiel, jeder Zyklus ist 1 Mikrosekunde, dann das ist zusammen 200 Mikrosekunden für das Programm. Okay. Aber das ist natürlich nur eine ganz hoch Niveau einzusetzen. So, wenn wir die Cycles per Instructions reduzieren, dann können wir auch die Möglichkeit dieser Programmlaufzeit zu verbessern. Für die zwei verschiedenen Maschinen, so für RISC, die Cycles per Instruction kann möglich ein bisschen größer als 1 zu erreichen. Für CISC es ist es schwierig, unter 2 Zyklen zu bringen. Okay, so wenn wir einfach Rechner entwickeln, dann jeder Befehl braucht nur ein Part Zukunft auszuführen. So, am besten können wir vielleicht ein Zukunft per Befehl zu erreichen. Vielleicht nicht genau ein, aber 1,01 oder 1,02 oder 1,5. Wenn wir ein kompliziert Rechner so mit CISC-Maschinen zu entwickeln, dann ist es schwierig, dass wir so geringe Cycles per Instruction Wert, weniger unter 2 zu bekommen. Okay? Deswegen, es gibt die zwei Möglichkeiten, RISC oder CISC, um Befehle zu erreichen. So, was ist die Eigenschaft von RISC? So, zunächst, die Befehlswertlänge sind fest. Das bedeutet, jeder Befehl hat gleiche Länge. Es ist mit Load- und Store-Architektur. So, wir laden zuerst die Datei und Befehle zu arbeiten und dann am Ende, wenn wir die Datei im Speicher zu schreiben, dann machen wir Load Storeword. Es gibt auch einfache Adressierungsarten, so zum Beispiel Indirect Adressierung ist manchmal auch nicht erlaubt. So. Und dann ist die semantische Lücke zwischen Hauptsprache und Assembler-Befehle kann man durch Compiler überbrückt. Das bedeutet, wir haben nur wenige Befehle und diese Befehle sind vielleicht nicht genug, um alle Anweisungen zu realisieren. So, vielleicht wir brauchen mehrere Befehle, um eine Anweisung zu realisieren. Und natürlich, wir schreiben nicht einfach alle Befehle mit Hochprogramm, aber wir können einfach mit Compiler diese semantische Lücke zu überbrücken. Okay? So, es bedeutet, wir brauchen meistens Aufgaben von Software. So, die Aufgaben von Hardware ist einfacher. Okay, so, und es ist deswegen einfach Hardware realisierbar mit nur weniger weniger Typen von Hardware. Es ist einfacher zu realisieren. Okay? Gibt es Fragen über RISC? Okay, so, dann habe ich eine Frage. Welche Frage ist es? So, ist RISC 5 ein RISC oder ein CISC? Well, it seems a stupid question, but yes. So let's go back. So RISC 5. RISC 5. Let's check whether it has everything we have here. RISC 5, in our lecture, we talk about 32-bit RISC 5. That means that every instruction has 32-bit length, no exception. When you load an instruction, the instruction has 32-bit. So, first one, check. If you want to read the data, you cannot directly access the memory. All right? You have to load the data to the register, and in the end, if you write the register back to the memory. It's based on a load store architecture. It's a simple address. So you load the data from the specific address. You jump to the address with a simple addition. So you don't have indirect references many times. Okay? So you only have a few instructions. At least we learned only a few instructions in the lecture. And it seems that we can implement everything. So you can actually do that with all the rest. Right? So you can have the compiler to set it. So RISC 5, despite the name, it's actually a RISC architecture. Right? So hopefully this is not too strange. It's a, I don't know, it sounds like that I'm making a joke of this question, but it's really a RISC. Okay? So, which processors you know as RISC? Can you give me some examples? Anyone? Which processors are RISC? Don't Google, don't use Wiki. You cheated, so that's not. Yes. Which one is RISC?
I think ARM processors are RISC.
Which one?
ARM.
ARM processors.
Yeah.
Okay. That's right. What else? So your smartphone, is that a RISC or CISC?
My smartphone.
Yes.
It's RISC.
A RISC because? Which processor is that?
Apple? iOS?
Yes.
It's iOS.
iOS is an operating system.
I don't know. What is iOS?
I think it's an ARM processor. Huh?
I don't know.
Okay. The Mac. Who has a MacBook here? No one has a MacBook. MacBook M1. Which processor is this? That?
Auch RISC. That is RISC processor.
It's a RISC processor.
No.
Okay. Does anyone have a Mac Pro that is not M1? Not M2? What is that? So your laptop looks like M2 or M1.
It is an Intel processor.
Intel processor?
Yes, i7.
i7. Yeah. So is that a RISC or a CISC?
I don't think so. I think it's a CISC processor.
It's a CISC processor.
Yeah.
Lost my microphone. Hello? Okay. Did I accidentally close it? Thank you. Okay, so RISC versus CISC. So CISC. CISC was created at a time when there was no nice compilers. So you want the high programming language to be as close as possible to the hardware. So if there is a instruction, so if there is a type of a statement in a programming language, you want to have one instruction in the processor. You don't care about any log store architecture. You don't care about any instruction length. I just want to have one instruction per statement. Sounds very reasonable, right? So everything that you have in a hardware programming, you should have instructions that can match to that hardware that instruction. So then every instruction needs to potentially do a lot of things. Originally, in the RISC processors, you could somehow map multiple instructions to achieve one statement in the programming language. Now, in the CISC, you just say, well, let's not do that. Let's just use one instruction. Okay, so that means that if you have some uncertainty of your statement, you would try to achieve that by using a more complex hardware architecture to do that. So therefore, the instructions are more complicated or more complex. Okay, so how does that look like? There's one example. So Motorola 68000. It's also the first processor of the 680 series of Motorola. So let's look at a simple instruction from that CISC processor. So the move instruction. The move instruction moves something from the source register to the target register. Very simple. I move something from the source register to the target register. But it allows complicated operations. So the length of the word can be different. So you can operate that on the level of byte, on the level of word, on the level of double word. The word is 16-bit, double word would be 32-bit, depending on how much you want to move. And then you could have different modes in the target and the tier register. So let's have a look of the modes that you could have. You could do register address movement. So that means that you are not moving only from the data of a register to another register. You are moving the data pointed by the address stored in the register to the register. Okay, instead of loading the data first to the register and then move the data to the target register, you try to load the data directly from the address pointed by the source register to the target register. Okay? And of course, with this option, you can also move the data you can also copy the data pointed by the source register in the address to the address pointed by the target register. Okay? So you can have different types of addressings you would like to have in this instruction set architecture. I'm not going into the details here because it's just a lot of options you could have. Which one do you use? You can specify that in the modes that you want to specify in the registers over here. Okay, so if you look at the CISC architecture, then you could have different instruction lengths per instruction. So what you could get is that you could somehow have relative compact coding of the program. In a RISC machines, you have to use multiple instructions to achieve one statement in a high-level program. For the CISC, you can simply use the coding you have seen earlier to move the data from the memory to the data in another memory address. In the RISC architecture, you first have to load the data and then store the data. Right? You need multiple instructions to achieve that. Now with the CISC architecture, you only need potentially one instruction to do that. So with that, you have relative compact coding program. But you pay for a cost that every instruction now requires to decode the actual behavior of this instruction, because it's not very clear at the beginning of this instruction whether you need to operate for a specific instruction or not. You need to have micro instructions or micro operations for one instruction. So this implies that you will need more cycles to actually finish one instruction. So the number of cycles per instruction is usually large. So you need to have a program to interpret what you actually need to do with that concrete instruction. And the compiler can potentially not use all the instructions, so you would somehow need specific compilers to do that. Okay? Good. Any question about CISC? Wrong. Can you pass that? I started with a wrong position.
So generally, which type of RISC or CISC? So which type of the processors?
This is a question I'm supposed to ask you.
Like which is one the most popular for processors?
Give the microphone back to me. Because this is my question to you. Which one?
I think that right now is more popular RISC because right now we have better compilers. So I believe that because of that, RISC is probably better. Also CISC, it needs like special compilers, which are probably not so usual, not so popular.
Before we answer this question, let me ask you a few more questions. That's a good statement, but we would have other counter statements as well. So when do we use CISC? This is with multiple solutions, multiple answers. Okay, so let's try to vote. So whose laptop is with CISC? If you have Intel processors, it's CISC. If your laptop is with Intel processors or AMD processors, then that are CISC processors. Okay, so whose laptop is with RISC? If your laptop is Apple M1 or M2, then that's RISC. 1, 2, 3. So you're not. So the CISC processors are still more popular in the laptop business and the desktop business. Okay. Whose phone is with CISC processors? Barely none, right? Whose phone is with RISC processors? If your phone is with ARM processors, if you have no idea what I'm asking, check what your phone has. Or RISC-V, that would be RISC processors, okay? So now it's a nice question, right? So when Apple started to build M1, 2 years ago, I think, or last year?
3 years?
No.
I think it's 2020, right? I think it's
2020?
first M1, then M1.
Yeah, when was M1? 2020 or 21? Okay, I'm sorry. I think I bought one almost immediately, but I forgot which year. So when Apple started with the M1 business, the biggest question was the software compatibility, whether they could have sufficient softwares executing on Apple M1. And they managed to do that. Without that, it was impossible for users to run their favorite programs on the Apple Silicon. And since then, the business model has been changed. The desktop processors are no longer only CISC processors. The software developers have to develop for both of them if they want to be included in the Apple Silicon business model. Okay? So, but if you design a software that is only compatible with RISC, then you would have no possibility to do that with Intel processors unless someone ports that. So the compatibility is very important. Okay? So when you use CISC, one biggest reason is that this is the biggest reason. Okay, so what else can be? So, because I mentioned earlier that it's possible that it's more efficient. Right? So some programs can be easily transferred. You have the nice mapping between the instructions and the high-level programming language. And you can somehow optimize that. For example, Intel compiler can optimize the execution for the compilation for Intel processors, but you need to pay for it. You can sometimes use GCC to compile a program. It runs quite slow, but with you modify with the Intel proprietary compiler, it can become faster. Okay, so you need to somehow optimize for that. What's not correct is that although CISC has more instructions, it doesn't mean that you can run more programs. Both of them are Turing complete, if you can have a program executed on CISC or RISC, you will be able to run in the other ways in terms of semantics. The last one, so what was the motivation that Apple started with M1 or M2? Compared to M1 and M2, so M1 advances the state of the art 2 or 3 years ago. For which purpose? Apple must have a good reason to do that, right?
It is much cooler and much efficienter.
Much efficient in terms of speed, energy consumption.
Yeah.
Energy consumption and cooling. Anything to add?
Also, the royalty dropped because they paid royalty to Intel, not from ARM. They paid 50% okay, that's more business. Per processor added to the Mac, they pay €2 or $2 royalty to Intel, but with ARM they pay 30 cents per unit royalty to ARM holding.
Not technology reasons, but cost reasons. So, in general, that's also the reasons why your phones are not with CISC processors, because they consume more energy in general. And they may end up with also higher temperature. So if you use your phone with high temperature, your phone is barely usable. So you should not. Therefore, in the current state of the art, even the CISC processors are implemented using RISC processors. I'm surprised that my slides are not complete, but maybe I can see what I have left. I don't think we have left. Yeah. So we missed one slide here because you don't necessarily need to implement the CISC instructions using a CISC processor. You can decompose a CISC instruction into multi-port micro operations. And the execution of those micro operations are actually RISC processors. And this happens now in Intel processors and AMD processors. So the internal executions are done using RISC processors. Only the interface between the hardware and the software is still CISC processors. Is that clear? I could ask Guillaume from Debuggen. I could add that slide on Wednesday to explain this in a more detail. So that means that because of the complexity of CISC processors, it's very difficult to realize the CISC instructions purely by using such microprograms for interpretation. The state of the art is to implement this one using RISC microprocessors in CISC processors. Okay, good. So next one. Was spricht dafür, einen RISC-Prozessor zu verwenden? So I think the first answer is wrong, right? I mean, it's not always faster. It's not always faster. The processor is easier to construct. The third one is correct. Right. The last one, die meisten eingebettete Systeme, Smartwatch, Steuergeräte im Auto, haben einen RISC-Prozessor, so kann man Compatibilität sicherstellen. So, das haben wir auch doch gesagt. Das ist auch richtig. So now we know that the first one is wrong, the third one is correct, the fifth one is correct. The third, second, and the fourth one, I also don't know now. I need to think. So the program is einfach here for risk.
Ja, ich glaube, dass die zweite richtig ist.
Richtig oder falsch?
Nee, richtig.
Richtig, ja. Und die vierte?
Also ich glaube, viertes auch richtig. Zum Beispiel bei Steuergeräte im Auto, das kann man nicht durch einfache Befehle machen. Deswegen stimmt das. Das ist.
Wir gucken mal. Hab keine Ahnung. We created this tool for fun. I think you are all right. So, the question for the second one is what it means by program. The program on RISC is always with compilers. As we said, you need a semantic semantic gap. So the semantic gap, I mean, it could be easier, but if your instruction, your statement needs multiple instructions to be implemented, you need such compilers. So programming is as I said earlier, 6 processors are easier to program because every instruction corresponds to one statement. Yeah? But of course, you can also argue that I don't need all the instructions there, so programming with RISC is also easier. It depends on how you argue, so I was not sure about that answer. Yeah. Okay. We don't have such ambiguous questions in the exam, don't worry. Okay. Now, finally coming to my question to you, or your question to me. Which one is better?
Ja, ich glaube nicht, dass einer besser als das andere ist, weil it depends on what we use it for.
Yes.
So the both are important.
Does this answer your question? Yes, okay. So it depends on which one you are using and which one you are you want to design your system for. Okay. This is what everything about this lecture. We try not to talk about something that is the best. We try to give you different trade-offs or different design philosophies. And we should not say RISC is better than CISC. They have their own advantages and disadvantages. It's similar to the big endianness and little endianness. You cannot say that big endian is better or little endian is better because it's the same question as whether you want to eat an egg from the thick side or what's the side? From the thick side or from the thin side? Thin side. This is Deutsch. So from the head or from the tail? I don't know how to describe it in English anymore. Anyway, so it's almost meaningless to discuss which one. Of course, what you can say now is that since all 6 processors are RISC processors inside, it should be a nature to build only RISC processors. But there was a history that people started to build 6 processors. And then 6 processors became the only processors at that time. And then later on, the others started to think about, wait a second, it's too complicated. Let's do the RISC processors. And then the RISC processors started with the weak side, and now they are taking the winning side. But due to the compatibility, the 6 processors will still be there for some time. Maybe they will still be there forever, or they won't be there in a few years. But this is not what we can decide. It's the business model, right? So when Apple started to build the M1 processors, the biggest concern from the community or the society was that whether they can run sufficient programs. That imply that whether sufficient programs can be converted from CISC to RISC. And if they did not succeed, this revolution would be gone. And then the RISC processors will need more time to rise again for desktops and laptops.
So this is like the programming language. It was developing by the time we had C and C++ and then Java. Is it like that? Like the old languages, and then we developed like CISC's old language, and then not language, but yeah. What's this? Yeah.
So the question is whether the RISC
Like
and CISC
development.
processors are like the development of programming languages. I would disagree with that one. The RISC processors and the CISC processors were designed for different objectives, right? One was designed to have a simple hardware. Another was designed to have a simple bridging to the software, right? So which one is better? At that time, at the beginning, it was not so clear, right? So now it becomes clear because we are facing a lot of problems for CISC processors due to the high energy consumption and high implementation requirement. It turns out that at this moment, 6 processors are more complicated, but maybe the 6 instructions are easier. Whether the internal structure should be CISC or RISC is probably now rather nicely answered that internal execution should be CISC or RISC. But whether the interface to the software should be RISC or CISC is still a question. Because CISC would only need would result in short programs, and RISC would result in longer programs. Yeah. In general. Yeah. So I think it's again, we should not say which one is definitely better, but we should be able to tell that for which cases, which one is better. Yeah. And there's a reason why we spend so much time here. And I think in the last few years, this comparison between CISC and RISC processors has been always in the exam. So I hope you will be able to answer them correctly. Okay? Any question?
Apple developed something called Rosetta compatibility layer that
Yes.
translated the CISC to RISC instructions. So is something like this feasible to do, so to say?
Okay, so now if you have a Mac M2 and you want to run some programs written for Intel processors, you need to have this Rosetta installed in Mac. That means that you can translate CISC instructions to RISC instructions in the execution, right? So yes, so you can try to match the CISC programs to be executed on RISC processors, but this is only for executability. You want to execute a program. It's not for the performance. So you need one additional layer to do the translation. It's basically the compatibility. Yeah. So if we did not have RISC and CISC processors in the past, then we don't need this layer. The reason why we need such layers, also the translation between big endians to little endians or vice versa, is all because we have different design philosophies in computer systems in the past, and you would have to somehow have such translations if you want to design them. Yeah? So I think this question has no answer. I don't know what we have here. Curious what we get from the answer. Oops. Yeah, so I think it's up to you. I think these both are correct. You just have to say because of what. Okay, any question for this? So the last one I want to talk is about interrupts. In fact, I'm supposed to give this lecture in German up to this moment, but I think, honestly, I did not expect I have to talk about RISC and CISC until Daniel told me that I have to talk about that, so I was unprepared. So I did not look at the slides. I was looking at the slides for the next year until the moment that I realized I have to talk about that. Seems that it was easier to talk about this in English. So decided to do that in English. But I hope you fully understand RISC and CISC processors. And the next one about interrupts is in the last few years never been in the exam for this lecture. And the reason is that this is usually too complicated. Did you give an exam for this lesson?
No, wait, did we include risk CIS? Did we include like risk and CIS in the last exam?
Oh, maybe not this one. Okay, so I had the impression that it's always there, but Daniel said it was not this time. But let's say it has a high percentage that it will appear in the exam. But these interrupts are not. The reason is that I think this is too much for first semester students. And the reason also is that the only way that you understand interrupts is to handle the interrupts by your own. And to handle interrupts on your, you will need to understand operating systems. You will need to understand some programming in the low level programming, and then this is usually not possible in the first semester. I think you will be able to do that in the 5th or the 7th semester of the master study. Then you are slowly able to understand the difference between the user mode and the kernel mode, the privileged mode and the non-privileged mode, and you will be able to do things right. But I still think that if we want to talk about computer systems, it's also not correct not to talk about interrupts. So we will talk about interrupts in a way that it should be understandable for you, But if you really want to handle interrupts correctly, join us. We would have a lot of crazy ideas, and we have been working a lot. Or attend my lecture of real-time operating systems. You will be able to program the clocks on your own, handle the interrupts, and then make your system crash. If you handle interrupts incorrectly, your system crashes almost by default. So you probably not want to do that. On your laptop, we would have some smartwatches for you to crash. So, okay. Interrupts. What do we mean by interrupt? During the execution of a program, there could be exceptional cases, exceptional situations, that your program has to be stopped, or your computer has to first handle the exceptions before it continues to run the program. Those are called interrupts. So in English, for example, you are doing something, and in between someone interrupts you, then the system has to handle that interrupt before you can continue. Okay, so interrupts can be considered as such exceptions are, for example, the arithmetic exception, for example, divided by 0, or invalid instructions, or invalid addresses, or the memory protection corruption. So for example, you have an instruction. So instruction, you take division, instruction register 5 divided by 0. That should be an exception. You want to run an instruction, you load the instruction, this instruction is invalid. You cannot find the OP code, so it should be an exception. You want to load the data from another program, from an address that doesn't belong to the user program, that should be an exception. If you want to access some data that you don't have the access right, this is an exception. So without interrupts, basically you have no protection on your computers, so you need to immediately handle such exceptions. So interrupts are basically jump instructions, right? So that means that when you receive the interrupt somewhere, you jump to a specific address to execute the instructions that should be used to handle the exceptions, right? So it's basically like that. You are embedding at every address a go-to instruction if the interrupt comes. Okay? So it means that interrupts corresponds to automatic call of procedures when you have faults or exceptions. So what you basically need to do is similar to the jump and nick instruction. So it's generated by the hardware. When there's an exception, the hardware generates a jump and nick instruction, and then you have to deal with all the registers. So you have to store the current context to the register, jump to that corresponding address for interrupt handling, and after handling the interrupt, it goes back to the next program counter. So let's read it again. Now you are at this instruction, and then you receive an interrupt. The interrupt forces you to jump to another address for execution. Before jumping to that address for execution, you need to store the context. You need to store the corresponding registers. Otherwise, your registers are polluted, right? And then you call jump and link to that specific address and then do the instructions. And at the end, you restore all the registers you stored before and then jump back to the instruction. Whether you jump back to the instruction that has an interrupt or to the next instruction depends on the context. Okay? So if it's divided by 0, you jump to the interrupt and then goes back. Whether that divided by 0 can allow you to continue execution is another story. You would have to exit. If you are calling something, it's a page fault. You don't know the page fault yet. So if it's a memory that you can tolerate this interrupt, it's continue with the next instruction. So whether the program stops or not, or it goes to the next instruction, depends on the semantics. Okay, so this is what's written over here. So the return address, in this case, is written in this so-called machine exception program counter, and then you can jump back to this one. So a little bit details of the interrupt handling. So if you have multiple interrupt sources, then you can define priorities. So which interrupt should be handled first, which interrupt should be handled later, is defined by the priorities. For example, ARM processors would have that. So when you are dealing with the interrupts, you can somehow first block the interrupts so that you don't receive interrupts back to back to back to back using interrupt handlers. So when you are handling an interrupt, you receive an interrupt, and then you are somehow handling infinite amount of interrupts. So what you typically do is that when you receive an interrupt, in the first step of interrupt handling is that you disable the interrupts so that you do not have to have recurrent and infinite interrupt handlers. At the end of the return, if you want to return from the interrupt service routine, you call the machine return. So basically, this is a special return instruction from interrupts. And the return address is also not the typical return address. It's in a special register called machine exception or program counter that you need to call it. Okay, so those are the big details. And what are the different types of interrupts we have to think of? There are two types. One is asynchronous, another is asynchronous. The synchronous interrupts implies that when you have the interrupt, you must handle that immediately. And such cases are, for example, the invalid addresses. You can also have asynchronous interrupts. There are the cases that you don't have to handle the interrupts immediately, but you can still wait a little bit to handle the interrupts. So for example, if you receive an interrupt from the keyboard, you don't have to handle the interrupts immediately. You can still delay the interrupts for a few milliseconds. The users won't be too
What if there are more than one asynchronous interrupts?
I'm sorry, I did not get the question.
What if there is more than one asynchronous interrupts, like a lot of them? Then how does it work? Like we handle all the interrupts like in queue, or yeah, basically.
I don't get a question well. So if you have multiple interrupts at the same time?
Yes, multiple asynchronous interrupts.
So what happens with multiple asynchronous interrupts? They are, okay, let me try to rephrase the question. So if there are multiple interrupts and they are all asynchronous,
yes,
how do we deal with them, right? So if the interrupts are asynchronous, you don't have to handle them immediately. But when you enter the interrupt handler, you will go through the interrupt sources. You check the interrupt sources, and then you can decide how you handle the interrupt sources, right? So if you say that this is a keyboard interrupt, let's say network interrupt, you can decide whether you want to handle all of them in one handling routine. Or you can say that let's handle the first one and then handle the second one in the next round. Both are fine. Does this answer your question?
Yes.
Okay, good. Yeah. So if it's asynchronous, you don't have to handle that immediately, but at some point you need to handle that. Otherwise, you would not be able to handle the event correctly. Huh? Okay, so the next question that was also relevant to what I discussed earlier already. If there's an interrupt now, should we handle the interrupt during the execution of an instruction or at the end of the instruction? So, during the execution of the instruction, there's an interrupt. For example, divided by 0. Should we handle this exception already in the middle of the execution or at the end of the execution? Let's say, what is the instruction division? You divide, so you have 3 registers. Register 2 divided by register 4 is stored in register 6. If register 4 is 0, register 2 divided by 0 is stored in register 6. If you handle the interrupt at the end of the instruction, your register 6 is wrong. Okay? It's something that you don't know. Okay? If you handle in the middle of the instruction, then as long as you know that register 2 divided by 0 has an exception, then you haven't written anything to register 6 yet. Okay. So, if you handle the instructions that need to somehow break the current instruction, for example, divided by 0, or the memory protection. So you are not supposed to read the memory at all, but you try to read some memory that you don't have the access right. You are not supposed to let this instruction finish its execution. Okay? You are supposed to cancel this instruction, or you are supposed to throw an exception in the middle of the execution. There are instructions that you can wait until the end of the instruction and then handle the execution. So, for example, those things that you have some external, those things that you need only asynchronous interrupt handlers would allow you to do that, because they are usually not severe regarding to the safety of the system. Okay, so if you receive interrupts, you also can decide. There are also possibilities that you have to stop the execution or continue. You can have the option to continue the execution. So if the instructions are not valid, or the address this is relevant to memory protection, then you should stop the instruction. You should stop the program immediately. But if you would have to the possibility for continuing the execution, then you can continue. There are some exceptions designed for the continuation of the executions. So for example, patch faults. The patch faults will be explained in the second or the third weeks in January. Those are designed to handle the memory hierarchy. So those are exceptions that were designed to happen automatically. And you would have to handle that to allow the program to have large memory space. And such exceptions are supposed to let the program continue. So this is the overview of the different interrupts. So we could have a look of them. So this is the input-output device. They are usually asynchronous. So you don't have to handle the keyboard immediately. So you can basically take any mouse events and keyboard events asynchronously. You don't need to stop the program, the instruction in the middle. If it's a system call from the operating systems, then it's supposed to be synchronous. Otherwise, you would allow the other instructions to be executed in the wrong operation mode. But you don't actually need to interrupt in the instruction. If you use debugging mode, you have the so-called breakpoint instructions. So it stops the execution of the program. It's supposed to be synchronous. Otherwise, you will not be able to do the debugging correctly. It's also not necessary to interrupt in instructions. The exceptions of computation, for example, the floating point exception, it's also synchronous, and you don't need to interrupt that in the middle. The timer. It sounds like the timer interrupts are synchronous, but it's not necessary. You can tolerate a little bit drift of your timer. Your system remains okay. It's just not exact, because any synchronization of timing is not exact, so you don't need this to be exact. Of course, you can force that to be synchronous if you would like. Then the batch fault is synchronous, and you could you would need to interrupt that in instruction. And you can also have a look of the others, the memory protection and the hardware failures. You could handle that both synchronously or asynchronously. And if your internet is not connected, it's basically not so important, right? Your computer remains functional. It's just not connected to the internet. So basically, you can handle that asynchronously, and you don't necessarily need to interrupt in the instruction. So in RISC-V instructions, in the examples you have seen in the programs and in the lecture, you will need to actually call a system call. This is actually implemented using eCall, so environmental call. You basically have to specify the parameters in a register. So what you actually do is that you make a instruction eCall, and then you have a service number, and the service number is stored in register A7. And in the ROS simulator, you can actually put the corresponding service number, and the corresponding arguments can be put to decide what you want to put. So for example, if the service number is 1, it prints the integer stored in register A0 or X10. If the service number is 5, it reads the integer and the output is put to A0. And if you put a service number 10, then this program exits from the loss simulation.
What if there is another number other than 1, 5 or 10?
Daniel, do you have a complete table? There are different numbers, yes. We only use the 3 because those are relevant ones to the service numbers we use.
And all these numbers, they are stored in this variable A7.
Yes.
And depended on what is in this variable, this is what will be executed if we call environment call.
Yes, that's right.
Okay.
So if you, this is only a subset of the service numbers. And of course, we only use those numbers you need it in the lecture so far. So if you want to continue, actually everything is there. You can also read a string. You can also output other stuff, but we don't need that. Yeah?
List, but I'm not sure.
There's a list.
I'm not sure where.
Yeah. Okay, so the reason why you need to do this is because with the simulator, we don't have operating system. So you will need to simulate a system call. So the system calls are actually simulated in ROS, and you would need those service numbers over there. Okay, so what's usually forgotten in the interrupt handlers is that you have to check whether your program can be re-entered. So that means that when you handle the instruction, when you handle the interrupts, it's possible that your interrupt handler cannot be re-entered again. So that means that during the interrupt handler, you cannot enter the interrupt handler again. Okay? So you cannot have nested behavior of your handler. So whether your interrupt handler can be re-entrant or not depends on how you use the registers. And since this is usually too much for the first semester students, I'm going to skip this one. So that means that if you look at the interrupt handlers, you see some strange declarations of variables. Some of them are volatile, some of them are not volatile. And if you want to understand which ones are volatile, which ones are non-volatile, you need to know which one is stored in the registers, which one are not stored in the registers. And the purpose of those is to make sure that your program is re-entrant. And if your program is not re-entrant, you have to make sure that your interrupt service routines blocks every other interrupt. Otherwise, your program would be wrong in handling interrupts. So let's skip this one. That's the basic introduction of interrupts. Any question of interrupts? It's nature that you will say, what the interrupts are interrupts. Okay. The problem is this one. Without interrupts, there will be no handling of input and output devices. Without interrupts, you will not be able to nicely handle the memory protections. Without interrupts, you will not be able to handle a lot of exceptions. Exceptions are always there. If you do not handle exceptions, then your system must be super pessimistic in the design. So, for example, you can allow numerical overflow, right? So we do not have to always check whether the addition of two registers is always correct. But if there's an overflow of the computation, you can ask the processor to generate an exception. But you have to handle that exception. So you don't want to always check whether the summation of two registers, two positive numbers, is always positive or not. You don't want to do that in software. But you can do that in hardware. If you do that in the hardware, then you need to generate one exception after that. You can say that the summation, this add instruction, generates an overflow. Okay? But then the system has to handle the overflow. And how do you handle that? It's by such interrupts. Okay? If you access the wrong address, if you don't want to protect the address for every instruction, otherwise, if you don't protect that for every load word, you need to check whether the load word reads the right address range or not before you load the word. Okay, so now you arbitrarily load a word from the address. Now you can check from the hardware, from the memory protection unit, whether this load instruction is loading the address from the valid address range. And then it generates an interrupt. So without interrupts, your system would not work at all. Okay? So interrupts can be considered as load and link everywhere, because the interrupts can come anytime. So now you can think about different handlings of the interrupts. And that's the reason why it becomes complicated, because you have to handle such interrupts from the user perspective to the system perspective. And that's the reason why it becomes complicated. So as I said, I think this is the right level of abstraction, that you learn something for interrupts, but you still don't know what the interrupts are because you haven't touched it. You haven't touched any interrupt handlers. But as I said, because of that, if we give that in an exam, it's going to be very superficial. So I will not test you the classifications of those stuff. But although I said that interrupts are not part of the exam, it's potentially part of the exam if it's combined with polling in terms of input and output strategies. The interrupt service routines we discuss here are not part of the exam, but later on in the last lecture, there's going to be some discussions whether you should handle the requests from the input-output devices using interrupts, or you should poll the input-output devices using polling. And you will need to understand the differences of these two. Okay, sorry, I make you more confused. So, if you don't want to implement interrupts, there's still another alternative. So you can always ask the I/O devices whether there's any data for you to read, or whether it's possible for you to write to the I/O device. So instead of waiting for interrupts from the keyboard, you can ask the keyboard buffer whether there's any data you need to read now. So you can actively ask the keyboard every microsecond, or you can wait to be interrupted by the keyboard that there's an input to be handled. So if you actively ask the keyboard whether there's anything you need to read from the keyboard, this is called calling. If you passively wait and being interrupted by the keyboard, this is called interrupt. And for this difference, we are not excluding from the exam. So for the interrupts I talked here today about different handling mechanisms, as I said, this is too much high level. I think it's only meaningful when you really do the interrupts from other lectures. But you should understand interrupts. Okay, so to conclude this lecture set, I would like to introduce the von Neumann model. So the von Neumann model was introduced by John von Neumann. As we discussed earlier, the two pioneers, John von Neumann and Alan Turing, designed the first generations of computer systems. John von Neumann had that design of computer systems using this abstract view that we have a processor, a memory, and the input-output devices. And these three components are connected by using networks. So this model, after being introduced in 1940s, remains valid up to now. So why is it still valid up to now? Let's have a look of our modern processors. So we have the processor, difficult, 7, the processor, no, Control L, the processor, which color can work? The processor, yes, okay. And then we have the memory. And we have the input-output devices by using PCI Express. Okay? So it's another personal computer. So where's the processor? This one? No. This one? No. In between? Isn't this a fan? Under the fan is a processor. Okay, this is a fan plus a processor. Where is our memory? Top left. This is the memory. Where is our input and output? Bottom left. This one. Okay. Those are the interfaces to external. Which ones are connected to the bus?
Then the PCIe consistor.
Where is the PCIe?
The black one in the middle. Yes. No. That's
These are PCIs. These are PCIe. Yeah. Let's not talk about the South Bridge and North Bridge. We talk about the South Bridge and North Bridge at the end of the semester, because we are talking about this architecture. we can expand this architecture. So the south bridge and the north bridge belong to where? You started south bridge and north bridge. Let's make this a bridge. So it's about networking. So you can, so although this seems very simple, the advance in the last years, in the last decades, was not to improve this architecture in terms of the schema. They improve the Verbindungsnetzwerk in the motherboard. Right? You have more complex architectures in the motherboard, in the I/O controller, from ESA to PCI to PCIe. Okay, so from IDE to SATA, those are all from the Verbindungsnetzwerk and the I/O controllers. But if you really look at the structure, the processors remains as processor, the memory remains as a memory. You can say that some memory is now part of a processor, but you still have the processor and the memory. And then you have a more complex interconnect. And you have different types of I/O controllers. But the whole schema remains as abstract as this von Neumann model in terms of processor components. So the von Neumann model for hardware design remains as a state of the art. Okay, so what is the von Neumann model? You have seen that. So the von Neumann model also says that the structure of the system is independent from the problem under study. The system is memory programmable. The execution, the statements, and the operandum is somehow stored in a memory, so as we have seen in a memory over here. And the memory is divided into the same size, and you can access that using addresses. So the execution of the program is composed of a sequence of element instructions, and then those instructions are executed in sequence, and then to execute from the memory. It's possible that you can jump from the execution. So if okay, so when you execute the instructions, it follows a sequence of binary bit vectors, and you can actually represent all the sizes you would like to represent. Therefore, you will need to have explicit. You don't have explicit representative types. You will need to declare the corresponding types in the von Neumann models as well. So what you have seen here is that if we look at the von Neumann processors and von Neumann models, the RISC processors actually fit this the best. And it also follows the whole architecture of von Neumann models. So that's it for the introduction of the instruction set architecture. So we talk about the models of computers and from different levels. We talk about assembly level and also the assembly level. We talk about the RISC-V assembler and also the instructions level. Let's compile. Let's translation from the programmer using assembly, and then also the instruction set architecture. We should also talk about. We also talk about the characteristics of the von Neumann machines over here. I don't know whether Professor Teuben explained you about the exam regarding the instruction set architectures or not. No? So there was always a question in this lecture whether you have to memorize the instructions at all, right? In the exam. Do you need to memorize? The question is always whether memorizing all instructions is necessary for the exam. The answer is that no. The reason is that due to COVID, we have developed our own instructions. And you will receive the menus during the exam. And this has been randomized to a degree, so I also don't know which instruction set architecture we will receive or you will receive. Of course, you can argue that what is the purpose of this? But I think.
Aber das sind schon die Instruktionen, die wir jetzt auch in der Vorlesungsreihe gelernt haben, oder?
Sorry?
Die Instruktionen, die wir jetzt behandelt haben, das waren einfach die wir in der Vorlesung gemacht haben.
Ja, das ist für die Vorlesungen und die Übungen, machen wir einfach RISC-V. Für die Klausur habe ich keine Ahnung. Aber Sie bekommen die ganze Instruction Set Architektur im Klausurblatt.
Das heißt, ist es dann irgendwie eine andere Syntax, die wir dann dort verwenden?
Ja.
Also es wird halt so sein, dass eventuell gewisse Instruktionen angepasst werden. Ja? Also es ist jetzt nicht so, als ob Instruktionen vorkommen, die was ganz Wildes machen, was ihr noch gar nicht kennt. Ja? Aber zum Beispiel kann es sein, dass wir eventuell so ein bisschen Twist geben, ja, so ein bisschen die Instruktionen anpassen. Es werden halt nicht genau die gleichen sein, so und nicht die gleiche Funktionsweise. Aber also zum Beispiel sowas wie ein Loadword oder sowas werdet ihr weiterhin haben. Nur wie gesagt, vielleicht werden die irgendwie anders, statt meinetwegen Zielregister und Source-Register und Offset gibt es meinetwegen vielleicht 3 Register oder sowas, die irgendwie anders funktionieren. Vielleicht werden die beiden addiert oder sowas oder multipliziert. Wer weiß, irgendwelche solche Spielereien. Ja? Oder vielleicht kombinieren wir Instruktionen oder sowas.
So, for example, in the lecture RISC-V, you will learn that you do multiplication. The result is only the low 32-bit, right? You multiply with 2 registers, the output is only the low 32-bit. The higher 32 bits would have to be loaded from another instruction, right? So we can create an instruction set architecture that allows you to put, for example, 5 registers. And then you could do you can do multiple things in one instruction. But it will still be RISC, okay? So it's just more creative in terms of the instruction set architecture. It's very likely not RISC-V, because then it forces you to also read the menu of the instruction set architecture. Okay? So, and now for us it's very easy to do that because during COVID we developed multiple instruction set architectures in random. So for us it's probably a button and we can generate different instruction set architectures with different instructions. So, what I say here is not like that you should not start it with 5. What I would like to say is that you should start it with 5, but you don't have to memorize those instructions because the purpose of this lecture is not assembly. The reason why we teach assembly in this lecture is because because you need those assembly to understand the subsequent parts of this lecture, to understand how you control the memory, how you control the microarchitecture in instructions. And without assembly, we are not able to talk about the later part of this lecture. But since the assemblies are so easy for giving you points for free, I would suggest you take all of them. And of course, this lecture started with, a few years ago, we gave this lecture based on MIPS. And then 2 years ago, we moved to RISC-V and happened to have COVID. And immediately, students asked me which instruction set would be in the exam. I said it would be none of these two. So it's fair for everyone. And of course, now you can challenge us, why do we still do our own arbitrary instruction set architecture? My answer is that this course, this lecture, is not assembly. So what we want you to understand is the hardware levels. You could have the assignment that someone creates some instructions architecture, and you are supposed to work on that, right? So for us, it's more about understanding. So you should be able to understand any arbitrary instruction set architecture, and then use that information to interpret a program and to understand the assignments. It's very important to read the assignment because we will use one instruction set architecture for almost the second part of the exam. So it's not only about assembly, but also the control of memory, also the input-output, cache, and all the relevant stuff. So read the instructions carefully, and read the instruction set architectures carefully. And if you have any doubt in the exam, ask the tutors, and hope that we have a complete instruction set architecture. Any question? If not, I will have my last lecture this semester on Wednesday. This Wednesday is not a lecture, right? This Wednesday is Weihnachtsvorlesung. So we have selected already 5 candidates for the most beautiful Christmas trees. And we also have some quiz on Wednesday. See you on Wednesday.